In this video, I will talk about the electric field due to a large metal conductor. So here we have a large sheet of metal conductor that is positively charged. The surface charge density is given here, which is 5 microcoulomb per millimeter square. And we have to find out what is the electric field at a distance of 5 millimeter. Okay. So how do we do that? So first we need to find out the electric field value, and there are different ways. You can use the Gauss law to calculate it, and here I'm going to derive it. Okay, so sometimes I see you confused whether to use E equals to sigma over epsilon naught or E equals to sigma over 2 epsilon naught. Okay, and I'll explain this one. So these are the formula for calculating the electric field due to a large sheet of conductor, and I'll explain whether to use sigma over epsilon naught or sigma over 2 epsilon naught. So first thing, let me tell you one thing here. So let's say you have a metal conductor here. This is a metal, okay, and this is positively charged. If a metal is charged, then the electric field only resides on the outer surface. So here the charges will only be on the surface of the conductor. Okay, so the electric field is always away from the surface here. If this is a positive charge, then this will be away here. And the electric field, there is no electric field inside the conductor, whether it is a solid conductor or it is a hollow conductor. There is no electric field inside the conductor. What does that mean? That means the electric field is always away from the surface. If this is a positive charge, and if it is a negative charge, then it will be towards the surface, but it cannot penetrate into the metal and come inside. So the electric field cannot penetrate the metal. Okay, so the electric field is always away from the surface if this is a positive charge. So what does this mean? This is the electric field inside. This one is 0. So now coming back to the same thing here. So in this case, at this point, the electric field will be away from this charge here, and there will be no contribution of the electric field if it is charged on the other side. So the only contribution of the electric field at this point will be coming from this side only, even if it is charged on the other side. Okay, so let's now find out the electric field down. So in order to find out the electric field, I'm going to use Gauss law here. Okay, what does the Gauss law tell you? Is the total flux passing through a closed surface is equal to Q enclosed by epsilon naught. So this quantity, the integration of E times dA, is the total flux. So this total flux passing through a closed surface has to be equal to Q enclosed by the Gaussian surface divided by epsilon naught. So here I'm just chosen an imaginary Gaussian surface here in the form of cylinder. Okay, you can choose any arbitrary surface, but if you choose any arbitrary surface, then doing the integration will be extremely hard. Okay, so in this case, the most simplest case is the cylindrical case. Okay, so, or you can choose, in fact you can also choose a cubical shape too. Cubical, it doesn't matter whether you choose a cylindrical surface or a cubical surface, it should be exactly the same. Okay, so now I have chosen a Gaussian surface here. First thing, we have to find out what is the charge enclosed by this Gaussian surface. So the only charge that is enclosed by this Gaussian surface is by this cross section here. Okay, so the amount of charge that is enclosed by this Gaussian surface is given by sigma A. Why sigma A? So So sigma is the surface charge density, which means the charge per unit area. So if I solve for charge, it will be sigma times A. Okay, so and A is the cross-sectional area here. So this is the cross-sectional area here. So we know now the charge enclosed. And now let's find out the total flux passing through this closed surface here. So due to this charge here, the flux will be passing this way. Okay. So the only flux that is passing through is this circular cross section. There is no flux passing out this way. There is no flux. The only flux that is passing is this way. So if in order to find out what is the flux passing through this cross-sectional area, we need to know the area and we need to know the electric field. So here the electric field is a constant, or the electric field just passing through this one is, let's say, E, and the cross-sectional area is A. And in this case, there is no, the electric field and area vector are both parallel. So it will be simply E times A. If I look through this surface here, this is the area vector and this is the electric field vector. So the angle between them is 90 degrees. So why the electric field is the parallel at all points? So electric field is always perpendicular to the surface. If I choose at any point, the electric field is parallel in this case. Okay, so it doesn't matter at which point you choose electric field, the electric field and the area vector are always the parallel. So the total flux that is passing through the cross-sectional area is E through this cross-sectional area. So this is the LEA, the total flux. So you might be wondering, so there are two cross-section here. So why I'm not choosing 2EA? So the reason is, whatever the flux passes through this cross-section, the same flux passes through this cross-section here. Okay, so there is no any extra. So this, whatever flux passes through this circular cross-section, the same flux passes through this cross-sectional area. So the total flux that is passes EA, and we already have calculated the charge enclosed, which is sigma A divided by epsilon naught. So E is now sigma over epsilon naught, and if we solve, then this is the number we get. Now let's see. Now let's talk about when do we get sigma over 2 epsilon naught. So if you had a charge, let's say just a sheet of charge, or a charge on an insulating material that is uniformly charged, or a better I would say this is just a sheet of charge. Okay, then the electric field at this point, the electric field due to this charge will be on both sides. So as it looks like, the electric field is emanating on both sides here. Okay, so in this case, the electric field value you will get is sigma over 2 epsilon naught. All right, but if you have a metal conductor, then the electric field is always sigma over epsilon naught. Okay, so this is it from this problem, numerical problem. If you have any questions, let me know. And please do not forget to like, share and subscribe the channel. Thank you very much.